A very good morning to everyone. On behalf of the Department of Civil Engineering at SRM, I, Dr. Ruchika, warmly welcome you all to day 2 of our ongoing faculty development program, that is Sustainable Construction Practices in Civil Engineering. It gives me immense pleasure to introduce today's distinguished speaker, Dr. Arshdeep Singh from the Department of Civil Engineering, Punjab Engineering College. Dr. Arshdeep is a respected academician and researcher in the field of sustainable construction, known for his deep insight into green infrastructure. We are truly honored to have him. Without further delay, I invite Dr. Arshdeep Singh to kindly begin his session. Thank you.
Thank you so much, ma'am. Am I audible to you?
Yes, sir. Yes.
Okay, but I don't know why. Am I visible also? Is my camera on? I think there is some issue. Okay, let me share my presentation screen.
No, sir. Your camera is off, I think. Yes, sir. Now.
So is the screen visible, ma'am?
Yes, sir.
Okay, okay. So good morning, everyone. So my name is Dr. Arshdeep Singh, and I'm working as an assistant professor in Civil Engineering Department at Punjab Engineering College, Chandigarh. So today's topic of my presentation is potential of agro waste ashes in the production of sustainable concrete. So, so this I have prepared this presentation or lecture, I can say, for the current students who are in MTech or in PhD or want to who pursue their career in research and in sustainable concrete research area. So I think that this will be helpful for you. So if I introduce that agro waste ashes, so we know that India is second largest producer of rice crop and the second largest producer of sugar cane worldwide, and other variety of, we can say, agricultural crops are being produced in India, and the leftover of such type of agricultural crops. So these are burnt in the industry these days. So as a fuel, we can say, in the cogeneration plants. So the waste of that process, we can say, is ash. So so which again we can say is available in a huge quantity in our country. So I have just prepared today's lecture so that we should be aware that what type of ashes are available related to agriculture field. So we basically classify it as a biomass ash. So if we see that biomass as a fuel in power cogeneration plants, why there is a requirement? So on the left hand side, in figure 1, if we see, this basically shows the CO2 emissions based on sector usage in India. So the data is around 2020, but if we see the recent data, it is close to 50% that power sector in India. So it generates 50% of the total CO2 emission in India. And in this power sector, approximately we can say 45 to 50% is contributed by the coal combustion. So in the, we can say, in the for the production of electricity or any other industrial processes. So to we can say, to overcome this, government of India in a United Nations climate change conference which was held in Paris in year 2015. So some goals were shortlisted, we can say. One of them was that increasing cumulative electricity generation from renewable energy sources to 40% by 2030. So basically, Government of India is taking initiatives to use this resource, to use, we can say, this biomass as a fuel in various sectors for the production of electricity or in the power generation or co-generation plant. So another major step which was taken by Government of India, here it is highlighted in the point 3 that the Union Ministry of Power, while presenting the union budget in February 2022, mandated 5 to 10% co-firing of biomass at every thermal power plant in the country. And I think most of the power plants, it is uh, in progress now, that they use 5 to 10% of biomass as a fuel in combination with coal. So if we see the total installed capacity in India, total installed power generation capacity, it is close to 400 gigawatt. But if we see the current biomass power cogeneration, so it is very small as compared to the coal. So we need to, government of India is, though government of India is taking initiatives, but still we have to do a lot in this area. So this. As we know that CO2 generation, CO2 emissions are increasing worldwide and in India also, and cement industry is also a part of it, or we can say construction industry is also part of it. So in order to curb this CO2 emission in this cement industry, or we can say in the construction industry, we need to adopt some sustainable practices, uh, or the practices which are, we can say, sustainable in nature, or we can say we have to use or we have to reduce the use of fossil fuels, or we can say we need to reduce the depletion of natural resources and use the other resources which are available with us in order to make the process more sustainable. So that is why I say that for the production of sustainable concrete, these ashes may be helpful. So in this graph, this is bioenergy potential in India. So which was given by a study in 2014. So this is surplus biomass energy potential in megajoules. So if we can see here that in Punjab and Haryana region, it is there is the highest surplus biomass energy available among the India. Uh, so if we compare it with the other states, so again, this is further one data which I have taken from there is one institute, Sardar Savan Singh National Institute of Bioenergy in Punjab. So from there I have taken this data, and the bioenergy potential on the left hand side in this figure 3, if we see, this is surplus biomass available in India, quantity in million tons, and on the right hand side, if we see, this is surplus biomass power potential. So on the left hand side, if we see that India is covered with this green color, so which shows that surplus biomass availability in India is in most of the cases, we can say in every state in India, except this Himachal Pradesh, J&K and Uttarakhand, or on the east side, we can say Arunachal Pradesh, Nagaland. So except from few states, in most of the states, surplus biomass is available with us. And on the right hand side, if we see, this is surplus biomass power potential, that from that surplus biomass, if we use that surplus biomass for the energy production or in the cogeneration plant, so huge amount of energy can be produced from this biomass. So when we are going to, let us say, use this biomass, the waste of that process will be in the form of ash, or byproduct, we can say, will be ash. So different type of agriculture residues are available in India, like from the cereal group, from the oil seed group, from the pulses, sugarcane, other horticulture crops like banana, coconut, or jute, cotton. So if we see broadly, from the rice, from the wheat, or from sugarcane, so and cotton also. So these are the potential crop residues which can be used as a fuel in India, as a full, or we can say as a partial replacement of coal. So how does biomass compare with fossil fuels? If we see that, can we use these biomasses uh, as a fuel in the industry? Yes, because if we see or if we compare in this table, the calorific value of selected biomass and coal is highlighted to you. So if we see here, the GCV value of this bituminous coal, or we can say sub-bituminous coal, so it comes in the similar range as when we compare it with the some of the biomasses like rice husks, sugarcane, bagasse, or wood chips, we can say, or sawdust, we can say, corn cobs, or cereal husk. So the GCV of these biomass, so it is more than we can say 3500 to 4500 kilocalorie per kilogram. So which is good enough to be used as a fuel. Then we see that some treatment can also be done, like in the form of leaching, in which washing of the raw biomass with water or acid is suggested in the literature, or torrefaction or pelletization. Basically, we can say that can be done in order to increase the calorific value of that biomass. So, co-firing of more than 20% of biomass in terms of energy content is technically feasible as reported in the studies. So, but depending upon the plant setup and co-firing technology, as we know that different co-firing technologies are also there. So, substitution of more than 50% of coal can also be achieved. It is reported in these studies. So, but we need when we talk about a new technology, so some guidelines should also be there. So, by the Central Electricity Authority, Government of India, New Delhi, so they have prepared a draft for the technical specification for agro residue based biomass pellets for co-firing in coal based thermal power plants. So from here one can see that how it should be used, what should be the percentage, or what should be the calorific value of the fuel. So it is highlighted over there. So torrefaction basically improves the grindability, pelletization, and also make biomass resistant to microbial colonization. So what is torrefaction? Basically, it is heating in the absence of oxygen at temperature of 200 to 300 degrees Celsius for 1 hour. Then charcoal-like this substance is created, uh, which has less moisture content as compared to the raw material, and the overall volume of the product is reduced, and further it can be densified. So then some challenges are also there in terms of these agro-waste species, that like in for some of the application they may have a low calorific value, they have low bulk density, that they are light in weight, so transportation issue can be there. Then fluctuation in seasonal availability, that like for example rice crop, it is grown for 2 to 3 months in a year. So depending upon the availability, so some in some states we can say that availability issues might be there, but uh, it has some good uh, properties also, or we can say it can be used in the as a replacement in cement, that I am going to discuss later on. So this slide basically shows the cement production capacity in India. So as we can see that the cement manufacture is reckoned to contribute about 7 to 8% of global CO2 emissions. And current India's rank in cement production as well as cement consumption is number two. And if we see the year-wise trend, so the production as well as consumption of cement is increasing year by year. So, so if we know that demand of cement is more, so it will consume more natural resources, or we can say we are going to generate more CO2 in future if we are if the demand of cement is increasing day by day in our country. So, what is the alternative? So this is one alternative, that the agro waste which are available in India. So some of them are highlighted over here. So like bagasse ash is there, sugarcane straw ash is there, wheat straw ash, corn cob ash. So rice husk ash is there, rice straw ash is there, groundnut husk ash is there, wood ash, and coconut shell ash. These are the some of the products that I have highlighted. Otherwise, there are few more available in our country. So So these are used, or these can be used, or we can say a government of India is currently using them, the waste of these products as a fuel in the industry, and the byproduct of that is agro waste ashes. So the use of this agro waste ash, when we can say partially it is replaced by ordinary Poland cement, it makes agro waste blended ash blended cement. So this diagram I have taken from literature. This was a review study. Uh, so so basically, the advantages of these agro waste ashes in cement are highlighted in this study, that sustainable for the production of sustainable cement, we can say, in terms of cost effectiveness, we can say, in terms of carbon footprint reduction, we can say, or in terms of high performance of concrete, or we can say upcycling of resources, we can use such byproducts which are available with us. We know that we are using fly ash these days, or steel slag these days in the cement industry. Yes, it is good to use fly ash, but if we see that if we in the long run, if we see is that the electricity production from the coal, so it is going to reduce, and we are going to use other renewable sources like solar energy, wind energy, let us say, or nuclear plants, or any other source of electricity production. And the availability of coal is also limited to us. So we should seek other possibilities that which are available with us, like the agriculture. Indian sector, Indian market is highly dependent on this agriculture sector, and the production of these crops will continue to grow for years, we can say. So this is the publication data on the agro waste ashes, that year by year we can see that publications are coming out, and India is contributing a lot uh, in this area. So requirement of agro waste ashes before using as a supplementary cementitious material. So from technical point of view, if we see here that we cannot use blindly any ash in cement, or we cannot blend blindly any ash in the cement. So we need to first check whether that material is has some pozzolanic property or not, or we can say that material is uh, having properties which are specified in our Indian codal guidelines, or any other American or ASTM like codal guidelines. So we have to check, or we have to first characterize that material. So if it follows the Indian standard guidelines, then only we can use it. Otherwise, there is a restricted use, or we cannot use, we can simply say. So as per Indian code, if we see IS 269, 2015, so the requirement of reactive silica in the rice husk ash, so it is 80%, and pozzolanic activity index, it should be 90%, and loss on ignition, it should be limited to 5% only. So these requirements demand controlled combustion of rice husk in the industry. Then only reactive silica of this much high amount, 80%, will be generated, or we can say loss on ignition of this small value, that is 5%, will be achieved if there is controlled combustion of rice husk is done in the industry. Otherwise, it is not possible, or it is difficult to achieve. And then physical and chemical properties in table 4, these are the guidelines which are set by the ASTM C618 for the class N or pozzolanic materials. So we can see here that percentage of silica, alumina, and iron oxide, it should be 70%. Then loss on ignition here is 10% instead of 5% in Indian code. So it is a bit relaxed, we can say. Then finest requirement is there, that the that 66 percentage of particles should pass through 45 micron sieve. So this requirement basically demands, we can say, grinding of the material. When we receive material from the industry, after burning, we can say, burning of rice husk, or burning of sugarcane bagasse, or any other material. So these agricultural waste ashes have larger particle size, or we can say they are coarser, bit coarser in nature when we compare it with cement or other ashes. So grinding is the main requirement, or we can say the processing, which is demanded in the literature. So the basic mechanism of these waste ashes in the hydration of cement is similar to, we can say, fly ash, that these are rich in silica or rich in alumina. So in the primary hydration, we know that C3S and C2S react with water and generates calcium silicate hydrate gel. And in the secondary hydration, the calcium hydroxide, um, which is produced from the primary hydration process, so that reacts with the silica from the agro waste ashes and creates another or additional, we can say, a calcium silicate hydrate gel. So formation of this gel provides us or provide concrete or cement the additional strength. So this is the basic reaction mechanism in most of the cases. The ashes which contain good amount of silica and alumina, so calcium silicate hydrates or calcium aluminate hydrates are produced. Then development of biomass and co-fired fly ash specification. Yes, now here we are discussing about two different type of ashes. Like one is biomass ash, other is co-fired fly ash. So when we say biomass ash, what does it mean? It means that any biomass, which may be rice husk ash or rice straw ash or sugarcane bagasse ash, is solely burnt, or combination, we can say, is burnt in the industry as a fuel, and there is no coal. But in the second case, when it is burned in combination with coal, so we call it coal-fired fly ash. So as per Indian standard 3812, so this is for the pulverized fuel ash when only coal is burnt. But there is no fixed standard, no guidelines, we can say, right now for the use of this coal-fired fly ash or biomass ash. So can biomass and coal-fired fly ash meet the requirements of this standard? So this we need to check. Any other additional specification required to facilitate use of biomass and co-fired fly ash as a SCM? So this we need to check. This may include hydration kinetics, that how hydration of cement is going to change when we add these fly ashes, these we can say co-fired ash or biomass ash, or workability, how it is going to change, how setting time, physical property, how durability property like permeability, resistance to sulfate attack, or any other carbonation, let us say, it is going to change, how the structural properties are going to change. So that is so the in this area, a lot of study or a lot of research work is still required, we can say. So here I have just highlighted for a one type of rice as cash when we use as a supplementary cementitious material. So some physical, chemical, mineralogical, and morphological. These are valid for all other, we can say, type of agro waste ashes, like whether it is sugarcane gas ash or rice straw ash. So we check first its physical property, chemical property, mineralogical property, and then morphological property. So then these properties depend upon the origin and composition of material, then burning temperature of that material, and or burning or retention period during the combustion, that for how much time the combustion is done in the industry. So for the basically for the specifically for the rice sketch, it is very much important. As on the left hand side, if we see that due to incomplete burning, the color of this husk ash, so it was close to black, dark gray to black, we can say, when it contains 8 to 10%. And on the right hand side, if we see the RHA sample, which is well burned, so the color is very light as compared to the other. So aesthetically, the material is going to change totally when there is a good combustion. Then effect of burning temperature and residence time. It is clearly stated in the literature that when burning condition are going to change, like for example, burning temperature is going to be more than 800 for the rice as cash, and whole time is going to be more than 1 hour, we can say. So the mineralogy of the ash is going to change from amorphous to crystalline, and surface area of the ash again is going to reduce, as we can see here in this table number 5. At the bottom in figure number 10, this basically shows the XRD patterns of a rice cache sample when it was burnt at different temperatures, uh, like 500 degrees Celsius, 600, 700, and 800 degrees Celsius. So it can be visually seen that the number of peaks are going to be more when temperature was set at 800 degrees Celsius. And in this was a laboratory study, and we can see here that below 700 degrees Celsius, the mineralogy of the ash is mainly, we can say, amorphous. When I say amorphous, it means it has some glassy content, or we can say in simple terms that it is reactive in nature. So it will react with the silica in that ash, or alumina in that ash is reactive in nature. So RHA physical property, we see that the color vary from white, gray to black. So then specific gravity varies from 1.6 to 2.2. Average particle size of the as received ash from the industry, it is close to 100 micrometer or more than 100 micrometers. So this need to be reduced. And after grinding, we can see that in most of the studies, close to 50 micrometer, 5 to 50 micro or 63 micrometer particle size has been used. So then grinding is also required, because as we can see here that in figure number 11, that initial particle of rice husk ash, so it is porous in nature. It has internal as well as external pores. So when grinding is done, so these pores, the breakdown of these pores occurs. Due to breakdown of these pores, surface area reduces, and water holding capacity of this ash is reducing. So so the grinding of the ash is required in order to reduce the particle size of the ash. Okay, but still after grinding, the microstructure is porous in nature. These are the some photographs of raw, or we can say ground RHA. So we can see here that irregular shape particles are there, and the microstructure is very porous in nature. If we see the internal section of the rice cache. So so am I audible to you? Just let me.
Yes, sir. Yes, sir. You are audible.
Okay.
Yes, sir.
Just to confirm. Okay. So this from this morphology, this type of morphology, how it is going to affect the properties of cement. Like when we are going to add, let us say, 20% of this RHA in cement. So this due to this cellular morphology, so RHA will be having tendency to absorb more water. So if it is having tendency to absorb more water, when we are going to add it cement, so the standard consistency of the cement may increase, or we can say the water requirement in the ultimately in the concrete may increase due to addition of this RHA, addition of raw RHA, or we can say as received RHA. So due to which the grinding is required. When grinding is done, so the morphology, this morphology is going to change. And um, so as per the literature available with us, so it is suggested that grinding up to a particle size less than, we can say, 45 micrometer is required, so that it does not affect the water demand in the concrete. So RHA, this is the chemical composition of RHA. I think a lot of things I have discussed for the RHA. Let us discuss about another. So mainly it is rich in silica. If we see here on the first table, so in all cases, these are the results from the literature. So in all cases, mainly silica is the oxide which is present. After silica, in some of the cases, it is aluminum oxide, or we can say small amount of calcium oxide, but mainly it is silica. So these are the RHA obtained from industrial, XRD of RHA obtained from industrial and laboratory furnaces. So we can see here on the left hand side, figure number 14 and 15, they show the XRD pattern of the rice cache sample obtained from the industry. And on the right hand side, in figure number 16, it shows the XRD pattern of rice cache when it was prepared in the laboratory. So we can see here that even after burning for a period of 4 hours, the very few peaks are generated in the RHA in the laboratory. But on the left hand side, if we see the ash which we received from the industry, so it contains crystalline compound like cristobalite or quartz. It is, so these are basically non-reactive in nature. So they might be made up of silica, we can say, but that silica is not reactive in nature. So in industry setup, we can say the properties of the RHA which we are getting from the industrial setup, it may be different from the RHA which we are getting from the laboratory setup. So further, these are the chemical composition for the sample obtained from the industry. So we can see here in the major, the main point which we need to focus on, the loss on ignition, the unburnt carbon. So we can see here that in one case it is 8.55, 11, 8, 8 to 14, 2 to 15 range is there for different sample. Then 1 to 24 is the range for different samples. So in most of the cases, it is either it is close to 10% or higher than 10%. So in the industry, what does it mean? It means that we need to control the combustion conditions for the combustion of rices. Then further, the effect of grinding particle size and specific surface area. This is valid for all, we can say, other different type of agro waste ashes, like it may be sugarcane bagasse ash, that when we are going to grind it, more we grind, more will be the fineness. And the specific surface area, though it may increase or decrease because it has porous microstructure. So the uh, or the pores are going to collapse. And further, as we know that internal pores are also there, so new pores are going to develop. So the surface area in most of the cases it decreases with grinding, but it may increase also. Then chemical composition of RHA, and this is a comparison for sugarcane bagasse ash and rice cash. So we can see here the chemical composition of RHA and sugarcane bagasse ash is more or less close to each other, but the silica percentage or silica alumina and iron oxide percentage in RHA is slightly higher than sugarcane bagasse ash. And if we see the total alkali content or loss on ignition, so it is further slightly lower than the sugarcane bagasse ash. So which is good which is good, we can say that when we compare these two, so silica or alumina percentage should be high and alkali should be less, and loss on ignition should also be less. So it should be, we can say, within the acceptable range of as per IS codes. So so in this slide, I have taken some data from a review paper from the literature. So for the comparison of different agro waste ashes. So here different type of, we can say, agro waste ashes are highlighted, like sugarcane bagasse ash, rice husk ash, palm oil fuel ash, corn cob ash, coconut shell ash, and different other uh, agro waste ashes which are available in India. So these are compared on a single platform. So I thought I should show it to you. So this basically e-plot shows the chemical composition of different agro waste ashes. So on the left hand side, if we see here in this figure, the percentage of silica content is there. On the right hand side, the percentage of alumina content is there. So percentage of silica, if we see, so in RHA is the highest among all the agro waste ashes. Then it is we can say sugarcane bagasse ash or rice straw ash, or we have mm, this bamboo leaf ash. So, and on the right hand side, if we see uh, the alumina content, so alumina content is higher in this coconut shell ash, but in other ashes like bagasse ash or rice husk ash, it is varying from 0 to, it is below 10%. So, so in this case, so the main factor here is that if we compare rice husk ash with the product which we use these days, like microsilica or silica fume, though silica fume has high fineness as compared to rice husk ash, but the percentage of silica content we can say is close to silica fume. So this can be used, or I think it is in use in the industry that people are using in place of silica fume because it is much cheaper as compared to silica fume in the market. So then chemical composition of different agro waste ashes in terms of silica, alumina, and ferrite. So as per ASTM code, this total percentage for all three should be more than 70%. And in most of the cases, we can see here that the most of the ashes fulfill this criteria. And when we see the loss on ignition, so it should be less than 10%. We can see here that most of the ashes are below this line. So these are the trends. Basically, we can see that we cannot say that this is a fixed value that every time it will be. As I said it earlier, that everything depend upon the type of burning or how burning is controlled in the industry. Like it may be a open field burning or type of we can say facility like atmospheric fluidized bed boilers are there. Great type combustion is done sometime, or any other technology. It depends upon the technology. These days, cyclone bed reactors are there. So depending on the type of technology or type of burning technology, we can say the quality of ash will depend upon type of technology. Then morphology of different agro waste ashes, if we just compare on a single uh, page, so we can see here that irregular shape or cellular morphology can be seen. So in most of the cases, in or we can say most of the agro waste ashes, they have cellular morphology or irregular shape. When we compare it with the fly ash, so the fly ash has spherical shape particles, rounded in nature and very fine, we can say. So when we are going to use this type of ash in the cement, or when we are going to use this type of ash in the cement, like agro waste ash, so it is obvious that behavior in the cement matrix, or whether it is paste or mortar or concrete, so the behavior in terms of flow property is going to change significantly. So we can see here in this phase, in this slide, different level of, for the different level of displacement. This basically shows the relative slump after the addition of agro waste ashes. So in most of the cases, as we can see here, that slump is on the left hand side, on the negative side, and on the right side for it is for the a few of the cases, means when we use uh, when agro waste ashes were used, so slump was reduced when it was compared with the control mixes. So this reduction in slump is due to, we know that it is due to particle shape of the ashes or particle size of the ashes is, or we can say sometimes for the quantity, as we can see here, as the level of displacement increases, so the slump reduction is increases. So here comes uh, the concept of, we can say, rheology of concrete, so which is basically the science of deformation and flow of matter. So matter here in this case is concrete for us, and it describes the interrelationship between the force, deformation, and time. So normally applied to more or less fluid materials or material that exhibit a time dependent response to stress, like concrete. So, the rheology of concrete is going to change drastically when we are going to blend it with these type of ashes. So this figure basically shows that shear surface, and when we are going to lift the surface with an angle of theta, so a shearing force, let us say W sine theta, will be acting on the surface. So the laminas, fluid laminas, sliding over each other, will be subjected to different we can say velocity, or some, we can say, development of velocity gradient will be there in this case. So in this case, in, we can say, in shear flow, liquid elements flow past over each other, and velocity gradient come into the picture. So from this figure, if we see here, On the left hand side, for a solid material, the shear stress and shear strain behavior, if we see, it is linear, and it obeys Hooke's law, and the slope of it will give us elasticity. And on the right hand side, if we compare it with the fluid material, so in the fluid material, the relationship between shear stress and shear rate will be there, because velocity gradient has come into picture now. The rate of change of shear has come into picture for each internal fluid laminar. So the slope of this relation, if we see here, the slope will tell us the viscosity. Like in the solid case, we get to know the elasticity of the material. Now, for this behavior, we will get to know the viscosity of the material. The slope will tell us viscosity. So the fluids such as blood, food, cosmetics, and concrete, they show non-Newtonian. Yeah, this is for the Newtonian. Good example of a Newtonian fluid. This figure, which is shown in the blue color on the right hand side. But concrete is not a Newtonian fluid. It is basically non-Newtonian fluid. If we see here, it is more close to, we can say, we call it Bingham fluid, or or all cement based material, we can say, are Bingham fluid. Bingham fluid means that on the left hand side, or vertical axis, if we see that this is shear stress, on the horizontal axis this is shear rate. So for a Newtonian fluid, there is no force required to make it flow, but for a Bingham fluid or for a non-Newtonian fluid, some yield stress or some force is required to initiate the flow. So further, if we classify different types of rheological behavior, it can be, we can say, ideal Bingham plastic, or we can say it can be shear thinning with some yield response, like toothpaste is there, or it can be shear thickening. Shear thickening means, or we sometimes also call dilatant. Dilatant means that when we are going to apply a shear rate on the material, so it will become more thick, it will require more shear stress. And on the other hand, when we talk about shear thinning, it means when we apply a shear stress on a material, so it some thinning behavior will be there in the material. Like we have example, like even in concrete also, sometime with the addition of supplementary cementitious material, shows shear thinning behavior or shear thickening behavior, or sometimes it shows ideal Bingham plastic. So it depends upon the blend which we are going to use it in cement, that how it is going to change the rheology of the material. Then further we have different models, like for the linear flow model, for non-linear flow model, means like here in this slide, if we see the ideal Bingham plastic, which is shown in the red color, so it is linear behavior. But or blue, so these are the non-linear behavior. So similarly, so in order to interpret the data obtained from the, we can say, different type of rheometers, so rheological models are there in the literature, like Bingham model, Herschel-Buckley model is there, or modified Bingham model is there. So linear Bingham model is a more or less, we can say, a linear model, or very simple or easy to use model. And then when we say that more complexity in the flow behavior is there, some non-linearity is there, then we can use Herschel-Buckley model, or we can use modified Bingham models. So, so how to measure this rheology? Like this is one example. We can say this is a coaxial concrete rheometer, which is shown over here in this figure. That a computer is attached with a motor, and the motor further is attached with a vane, and vane rotate in a drum in which a concrete is placed, and the record of torque applied, and the shear rate is recorded. And then further, for example, if we see the next slide, so so these are the test protocol, basically, we can see. So on the right hand side, if we see at the bottom, so the relationship between shear stress and shear strain rate is obtained with the help of a instrument which is called rheometer, and this relationship in terms of torque and vane speed, and then further it is derived in terms of shear shear stress and shear strain rate. So the slope of this curve will give us the viscosity, and on the vertical axis, the gradient, this tau naught basically is representing the yield stress, that minimum stress which is required to initiate the flow of the material. So the main thing which I want to highlight here, so this was done by me, that the concrete which under investigation, let us say it is M30 grade, and so these are the result for the M30 grade, which in which 10%, 20%, we can say 15% RHA was added. So on the left hand side, in figure number 31, these are the torque and rotational speed results which were obtained from the rheometer, and on the right hand side, from these torque and n values, shear stress and shear rate was calculated from this equation, from the equation given in here in Bingham model equation. The first, from the meter, value is obtained in terms of T, G, H, and N. Then further it is converted to tau, tau naught, mu, and gamma. So mu basically representing the plastic viscosity. So we can see here that when we are going to add rice husk ash, add RHA from, let us say, 10% to 20%. So it is going to increase significantly. Although the yield value is same, because this test was performed for the similar slump value. So even if the slump value is same, the viscosity of the material for different percentage of RHA was more. So what does it mean? It means that more is the quantity of RHA, more will be the viscosity of the material, or we can say that this will make our concrete more viscous. So these are the dynamic yield stress and plastic viscosity values, that viscosity is going to change with the addition of this material. So uh, for the same material, if we compare the environmental factors like global warming potential or embodied energy, so it is going to reduce. We know that RHA is a waste material. So if we compare the global warming potential of the concrete containing RHA, so it is close to, we can say, 15 to 20% lesser than the plain cement concrete. So 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 in the nutshell, I would like to draw attention here that when we are going to use, let us say, fly ash or silica fume or GGBS or any other agro waste ash, so it is going to, we know we should have some idea that these material will definitely are going to change the rheology of the material, rheology of the concrete basically. So this should be taken into consideration while deciding the optimum percentage dosage. Then optimum processing strategies for agro waste ashes, which are highlighted in the literature. So broadly, they are, we can say, mechanical, thermal, thermomechanical, and chemical. Mechanical means some sort of grinding with the help of a ball mill, we can say it can be done on these type of ashes. Then we have thermal. Thermal means that, let us say, if unburned carbon in ash is high and we want to further use it, or we want to further process it, so it reheating can be done with the help of a small scale furnace or laboratory scale furnace, or if it is in industry, so industrial scale furnace, it can be done. Then thermomechanical, it is there that sometimes grinding as well as reheating is required. Then we have chemical treatment. So like leaching through water or leaching through acid is sometimes suggested in order to reduce the impurity of these ashes. So so, so what does it mean? From this slide, we can conclude that it cannot be directly used in the cement, these type of ashes. So need some processing in order to use in the cement. Then the benefit of it is that effect of like thermomechanical processing on pozzolanic activity. Here it is shown that pozzolanic activity increases with the addition of with this processing strategy. Similarly, improvement in compressive strength is found in the literature after the thermomechanical treatment. Then improvement in loss on ignition is uh, 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 visibly reported. We can see that here that acid treated and untreated sample, they have a huge difference in terms of loss on ignition in the laboratory. So improvement in durability properties like total charge passed in when the RCPT test was performed, so it was significantly reduced. Then we have other durability properties uh, for the optimal replacement level for different ashes. Similarly, we can see here the relative sorptivity value of the agro waste ashes, ash blended concrete was reduced. We can say that improvement in drying shrinkage uh, was observed when the agro waste ashes were used. Then similar to this, we can say a improvement in acid concrete under acid attack. So good we can say, or we can say the strength loss due to acid attack was reduced when these ashes was used. So overall, we can say the test methodology for any co-fired ash or any bagasse bottom sorry biomass ash. So it is that material characterization we have to do. Then pozzolanic reactivity we have to evaluate. Then we have to see whether it is satisfying as per the performance criteria of different codal guidelines, whether it is Indian or any other country. Then if it is yes, then we can use it as a supplementary cementitious material. Otherwise, we have to go through a suitable processing method, or we have to select the methodology which based on the characterization. We have to identify the methodology that only grinding is required, or grinding and some reheating is required. Then after some processing, we can use it in the we can blend it in the cement. So these days guidelines are there in the literature, but still if we see that uh, more more detailed guideline in the Indian code is still required for these issues. So concluding remarks, if at the end, I would like to say that it is essential. So, from the research point of view, these materials have a high potential for that. These more we do research, and more things will be clear to us. And it is essential to find barriers to the acceptance of these agro waste or co-fired fly ashes. Then categorization of different agro waste ash blended concretes with respect to their application is required. Then different processing strategies, other processing strategies need to be explored that might not be uh, very environmentally, we can say that are environmentally friendly. And then the absence of robust protocol for industry scale biomass co-firing are required. Then absence of specification, obviously performance standard for these ashes are required. So so identification of biomass, that which type of biomass is available in which region, the data is there, but still more in-depth study it is required in this area. So research-led application of agro-waste ashes or co-fired ashes or fly ash as a binder in cement-based material. So research-led application, like we can say that the output of the research or the research work in collaboration with the industry, we can say, is required. So this is from my side. Thank you so much. If you have any question, you can ask, please.
Thank you, sir. Thank you, sir, for the wonderful session. We have learned so much about agro waste ashes in cement, how agro waste ashes help in reducing carbon footprint, sustainable cement, and high performance cement concrete. We got so much knowledge about all these new things and about biomass, bioenergy. Thank you, sir.
Thank you. Thank you so much.
All the participants requested please turn on your cameras for the group photos. Please turn on the camera.
Actually, my system is new, so I don't know. I think some software is.
Thank you, all the participants. Participants will update tomorrow's session on the WhatsApp group.